Welcome to the Lesson 4 full video lecture. This week, I'll be introducing confidence intervals. Before we get into the new content, there are a few things that I want to review from earlier lessons because we'll see them again this week. In Lesson 1, we saw that inferential statistics are statistical procedures that use data from an observed sample to make a conclusion about a population. Confidence intervals are one of these inferential procedures. We're going to take data from a sample to estimate a population value. For example, we may have a sample proportion, p hat, and we can use that to estimate the population proportion p. Or we may have a sample correlation, Pearson's R, and use that to predict the correlation in the population, rho. When we do this, we'll construct an interval or a range of values that we believe are plausible estimates of the population parameter. These are all of the population parameters that we're going to be constructing confidence intervals for this week and their respective sample statistics. If you don't feel comfortable with these symbols yet, you should review these before starting this lesson because you'll see them quite a bit. Parameters are fixed values. For example, in the population of all World Campus students, the mean age is a fixed value. There is one mean age for this population and it does not change. It's often difficult or impossible to collect data from the entire population, so in many cases we collect data from a smaller sample. Data collected from a sample are known as sample statistics. Statistics are random variables because they differ from sample to sample. On the lab assignment in Lesson 2, you might remember when you took a simple random sample in Minitab Express, computed the mean and standard deviation, and then repeated. Even though all of your samples came from the same population, each sample had a different mean and a different standard deviation. Statisticians use what they know about how these statistics vary between samples to construct a confidence interval to estimate the population parameter. And that's what we're going to be doing this week. These are the learning objectives that we'll cover in this lesson. You might notice that StatKey shows up a couple of times. StatKey is an open access application. That means that it is free and open for anyone to use. We'll start with the first learning objective. Construct and interpret sampling distributions using StatKey. A sampling distribution is a distribution of sample statistics. If we were to repeatedly pull samples of n from a known population and record a sample statistic, for example, all of the sample proportions, means, correlations, even the difference in two means or the difference in two proportions, that distribution of sample statistics is known as the sampling distribution. The standard deviation of a sampling distribution is the standard error. We'll go to StatKey now to walk through a couple of examples of constructing a sampling distribution. StatKey consists of all of these different simulations. Later in this lesson, we'll be making bootstrap confidence intervals. First, though, we're going to be constructing sampling distributions. StatKey has sampling distribution demonstrations for a mean and for a proportion. I'll walk through one example of each of these here. They both use data from a known population to simulate what the distribution of sample statistics would look like. We'll start with an example of a sampling distribution for a mean. For all of the StatKey procedures that we'll see in this lesson, there are built-in data sets. We can also always edit the data. We can select all, delete, and then we could paste in our own data from Minitab Express or Excel. For this example, though, I'm going to use the second built-in data set, Statistics Grad Schools. Here we have all of the American universities with doctoral level statistics programs and their full-time enrollments from a few years ago. If I click Show Data Table, we can see the names of all of these universities and their full-time graduate enrollments. If I scroll down, we can see Penn State. This particular year, we had a full-time graduate enrollment of 75 students. On the top right, we have a dot plot of these population values. The population size is 82, and the population mean is 53.537. StatKey will also give you the median and the standard deviation. Let's say that we're doing a research study concerning graduate school enrollments with a sample size of n equals 15. The default sample size in StatKey is n equals 10, but we can click this and change the sample size to 15. Now, if I click Generate One Sample, StatKey is going to take a simple random sample without replacement of n equals 15 from the original population. This first simple random sample can be seen at the bottom right. In this first simple random sample of n equals 15, the sample mean is 45.667. This sample mean is plotted on the larger dot plot on the left. We can do this a second time. In our second simple random sample of n equals 15, the sample mean is 49.333. This value again is plotted on the larger dot plot on the left. The triangle and the number beneath it is the mean of all of the sample means so far. To speed things up, I can generate a few thousand samples. In this course, you should always take at least 5,000 samples to get a good picture of the sampling distribution. This large dot plot here is our sampling distribution. You could also call this the distribution of sample means. If we hover over any of these dots on the larger dot plot, at the bottom right, we can see that particular sample. The number at the bottom with the triangle is still the mean of all of the sample means. This should be similar to the population mean. We can also see the mean of the distribution here at the top right, along with the number of samples that we've taken, and the standard error. The standard error is the standard deviation of this sampling distribution. I'll go back to the main StatKey page to construct a sampling distribution for a proportion. Again, we have all of these built-in data sets. We can also edit the population proportion. Let's say that we're looking at the proportion of students in an elementary school class who are boys when all of the classes have 20 students. Assuming that boys and girls are equally split in the population, we should set this population proportion to 0.5. There are 20 students in each class, so n equals 20. On the top right, we see our original population with a proportion of 0.5, and we can see that we changed the sample size to n equals 20. Now I'll generate one simple random sample of n equals 20 from a population where p equals 0.50. In the first simple random sample, there were 7 boys in our sample of 20 for a sample proportion of 0.350. This sample proportion is plotted on the larger dot plot on the left. We can do this again. I'll take one more simple random sample. This time, there were 10 boys in this sample of 20 for a sample proportion of 0.500, which again is plotted on the larger dot plot on the left. The triangle and the number beneath it are still the mean of all of these sample statistics. I'll take 1,000 samples at a time until I've reached at least 5,000 samples. If we look here, we can see the number of samples that we've taken, the mean of this sampling distribution, and the standard error, which is the standard deviation of this sampling distribution. The procedures that we just walked through for constructing a sampling distribution for a mean and proportion only work when we know all of the population values. When we're constructing a confidence interval, we don't have the population values. We only have the sample values that we're using to make an estimate. In those cases, we can use bootstrapping techniques, which we'll see starting in the fourth learning objective. We'll go back to the PowerPoint slides now to summarize some of the terms that we've learned here. The sampling distribution is a distribution of sample statistics, for example, sample means or sample proportions, of the same size, n, drawn from a population. The standard error is the standard deviation of the sampling distribution. When we're constructing a sampling distribution with a known population, the mean of that sampling distribution will be approximately equal to the population parameter. We'll see this more in a later learning objective, but as the sample size n increases, the standard error decreases. And also, as the sample size n increases, the sampling distribution becomes closer to a normal distribution. These are true for all sampling distributions for any parameter. We saw an example using a mean and a proportion, but these are also true for correlations, the difference between two means, or the difference between two proportions. Remember that the procedures for constructing a sampling distribution that we just saw only works when we have the population data. Most of the time, we don't have population data, we only have sample data. In those cases, we'll use a procedure that looks fairly similar, known as bootstrapping, which we'll start to see in the fourth learning objective. The second learning objective is to explain the general form of a confidence interval. A confidence interval is a range of values which we believe contains the population parameter with a given level of confidence. The general form of a confidence interval is the sample statistic plus and minus the margin of error. The sample statistic we observe in our sample. This is your p hat, x bar, r, p hat 1 minus p hat 2, x bar 1 minus x bar 2, or slope of beta sub O. This is also known as the point estimate. It's the middle of the confidence interval. The margin of error is based on the empirical rule. You learned about the empirical rule in lesson 2. It applies to normal distributions. When we made sampling distributions in StatKey, you may have noticed that they resemble a normal distribution. As sample size increases, the sampling distributions will start to look more and more similar to normal distributions. According to the empirical rule, on a normal distribution, the middle 68% of observations will fall between plus and minus 1 standard deviation of the mean. The middle 95% of observations will fall within plus and minus 2 standard deviations of the mean. And about 99.7% of observations will fall within 3 standard deviations of the mean. This is sometimes referred to as the 95% rule because the most frequently used interval is 95%. Like we said before, the basic form of a confidence interval is the sample statistic plus and minus the margin of error. For a 95% confidence interval, which I'll often abbreviate as CI, that margin of error is going to be equal to 2 standard deviations. The standard deviation of a sampling distribution is the standard error. So we could write this as the sample statistic, or stat, plus and minus 2 times the standard error. Let's look at one example. A coin is flipped 100 times. The result is tails 54 times. This gives us a sample proportion, or p hat, of 54 over 100, or 0.54. StatKey was used to find a standard error of 0.050. Construct a 95% confidence interval. The general form for a 95% confidence interval is sample statistic plus or minus 2 times the standard error. For a single proportion, this would be p hat plus and minus 2 times the standard error. Our sample proportion was 0.54, and we were given a standard error of 0.050. 0.54 plus and minus the margin of error of 0.100 gives us a 95% confidence interval of 0.440 to 0.640. Our third learning objective is to interpret a confidence interval. Let's take the example that we just finished working with. We constructed a 95% confidence interval for the proportion of tails to be 0.440 to 0.640. To interpret this confidence interval, I would say that I am 95% confident, because remember that this is a 95% confidence interval, that the population proportion is between 0.440 and 0.640. In other words, given the population of all flips of this coin, I'm estimating with 95% confidence that between 44% and 64% would be tails. Let's walk through another example of constructing a confidence interval and interpreting it. How do men and women differ in terms of their heights? Height is a quantitative variable, and we're comparing two groups, men and women. So we'll be constructing a confidence interval to estimate the difference in these two population means. The mean of men minus the mean of women. In samples of 40 men and 40 women, men were an average of 7 inches taller than women. So X bar for men minus X bar for women is equal to 7. StatKey was used to find a standard error of 0.798. Construct a 95% confidence interval. For a 95% confidence interval, the general form is the sample statistic plus and minus 2 times the standard error. Our sample statistic here is the difference in the two sample means. Plus and minus the multiplier of 2, because this is a 95% confidence interval, times the standard error. Here, we're told the standard error was found using StatKey. Later, I'll show you how to find this standard error yourself. Our sample statistic of 7 plus and minus 2 times the standard error that we were given gives us 7 plus and minus the margin of error of 1.596 for a confidence interval of 5.404 to 8.596. To interpret this, I would say that I am 95% confident that the difference between the mean heights of men and women in the population is between 5.404 inches, and 8.596 inches. You may have noticed a pattern in how I interpret the confidence intervals. This is the general form of the interpretation that I use. I encourage you to use this as well, at least at first, when you're just starting to learn about confidence intervals. I am confidence level, so this will be a percent, typically 95%. Confident that the population parameter, so this will be your p, mu, rho, beta, is between the lower bound and the upper bound. The lower bound and upper bound are those numbers in the brackets that make up the confidence interval. So when I write these in brackets, it would be the lower bound, so the smaller of the two numbers, to the upper bound, which would be the larger of the two numbers. One last point related to interpreting confidence intervals. A confidence interval contains a range of acceptable estimates of the population parameter. Values in a confidence interval are reasonable estimates for the population parameter. Values not in the confidence interval are not reasonable estimates for the population parameter. Let's look at a couple quick examples. Using a representative sample of 112 World Campus Stat 200 students, a 95% confidence interval for the proportion who work full-time was computed to be 0.580 to 0.754. Is there evidence that the population proportion is different from 0.500? To answer this question, we're going to look at the 95% confidence interval to see if this value is contained within it. 0.500 would fall to the left of the confidence interval, so it is not contained within the confidence interval. Therefore, it is not a reasonable value for this population parameter. There is evidence that the population proportion is different from 0.500. Here's a second example. Data were collected from a sample of 20 inkjet printers. Their prices were recorded along with the number of pages per minute they print. A 95% confidence interval was constructed for the correlation, rho, between these two variables of 0.494 to 0.883. Is there evidence of a relationship between the price of inkjet printers and how many pages per minute they print? We have two quantitative variables, and the parameter of interest is the correlation in the population, rho. If there is a relationship in the population, then the correlation would be different from 0. Recall from lesson 3, when we first introduced correlations, that a correlation of 0 means no relationship. And as the correlation approaches negative or positive 1, the relationship is stronger. We're going to look at the confidence interval for the correlation to see if it contains 0. It does not contain 0, therefore 0 is not a reasonable estimate of the correlation in the population. Yes, there is evidence of a relationship between these two variables in the population. Our fourth learning objective is to explain the process of bootstrapping. Remember earlier, we used StatKey to construct a sampling distribution when populations were known, but I said that usually we don't have population values. Usually, we only have sample statistics. And in those cases, we can use bootstrapping methods to construct a sampling distribution. Bootstrapping is a resampling procedure that uses data from one sample to construct a sampling distribution by taking random samples with replacement from the original sample. A bootstrap sampling distribution is going to look very similar to the sampling distributions that we've already made. The difference is now, instead of randomly selecting cases from a population without replacement, we're randomly selecting cases from a sample with replacement. Sampling with replacement means that after randomly selecting a case, we put it back into the group from which we are sampling, so it is possible to select the same case more than once. Let's go to StatKey to look at a few examples. StatKey will construct bootstrap distributions for all of these different parameters. Here, I'll walk you through an example of constructing a bootstrap distribution for a mean and a bootstrap distribution for a correlation. In the online notes, there are additional examples for a single proportion and for the difference in two means. I'll start with an example for a single mean. As before, StatKey has some built-in data sets. The default is the Mustang price dataset. For this example though, let's say that I have data in Minitab Express that I want to copy and paste into StatKey to construct a bootstrap distribution for. I'll open that data in Minitab Express. The variable that I'm going to work with is height in inches. I'll select that column, copy, and then in StatKey, edit data. I'll select all, delete the previous data, and paste that height data from Minitab Express. There are two boxes below. First column is identifier, would mean that we would have two columns here. The first is an ID number or maybe a name, and then the second column would be the data. In our data set, we only have one column with no identifiers, so we leave this unchecked. Data has header row. It's checked by default. This means that our first row is the name of the variable, as opposed to the actual data set beginning in the first row. Here, our first row is height in inches, which is the name of our variable. So we'll keep this checked. We click OK. Our original sample now shows up on the right. Here we can see the sample size, mean, median, and standard deviation. The procedures now are going to look very similar to what we did earlier. We'll start by generating one sample. At the bottom right, we have our first bootstrapped sample. The randomly selected 474 observations came from the original sample. The size of each bootstrap sample is going to match the original sample size. In the bootstrap sample, there will be some observations that were selected more than once and others that were not selected at all. By doing this, it's simulating what natural variations we would expect to see. Since we don't have the population, this is like the next best option for constructing a sampling distribution. The mean of our first bootstrap sample is 66.644, and this is plotted on the larger dot plot on the left. Let's take one more bootstrap sample. Our second bootstrap sample of 474 has a mean of 66.652. Now we see there are two dots plotted on the larger dot plot. The triangle and number at the bottom is still the mean of this distribution. I'm going to go ahead now and generate at least 5,000 bootstrap samples to get a good picture of this sampling distribution. This is our bootstrap sampling distribution. Notice that it resembles a normal distribution. Like before, the larger the sample size, the closer to a normal distribution this will be. If we zoom in to the upper right of this plot, we can see that I've taken a total of 5,002 bootstrap samples, and this sampling distribution has a mean of 66.797, which is very close to the mean of the original sample, and a standard error, which is the standard deviation of this bootstrap sampling distribution, of 0.209. This is where we'll stop for now. In the 5th and 6th learning objectives coming up, you'll use two different ways to use this bootstrap sampling distribution to construct a confidence interval. First, I want to walk you through another example of just getting this far. For the second example, I'll construct a bootstrap sampling distribution for a correlation. Regardless of the parameter, the setup and the procedures are going to be very similar. Again, StatKey has some built-in data sets. For this example, I'll use the marriage age data set. In the top right dot plot is the original sample. I'm computing a correlation, so now there are two variables, husband's age on the y-axis and wife's age on the x-axis. In the original sample, n equals 105, which means that there are data from 105 husband-wife pairs. With two quantitative variables, StatKey will provide the correlation, slope, and intercept. The default is to record the correlation on the bootstrap distribution, but we also have the option of changing this to slope. For this example, though, I said I was going to construct a bootstrap distribution for a correlation. I'll generate one bootstrap sample, and this is the same procedure that we saw with one mean. StatKey is taking a random sample from the original sample with replacement. It is possible for the same observation to show up twice in this bootstrap distribution, and there will be some observations that don't show up at all. The correlation in the first bootstrap sample is R equals 0.935. This is plotted on the larger dot plot on the left. I'll generate a second bootstrap sample. In the second bootstrap sample, R equals 0.933, which again is plotted on the larger dot plot. To speed this up, I'll generate 1,000 samples at a time until I have at least 5,000 bootstrap samples. If we zoom into the upper right, I've taken a total of 5,002 samples. The mean sample correlation is 0.913 with a standard error of 0.017. I'll take you back to the PowerPoint slides now to show you two different ways that we can use these bootstrap distributions to construct a confidence interval. Our fifth learning objective is to construct bootstrap confidence intervals using the standard error method. The standard deviation of a bootstrap sampling distribution is the standard error, which we can use to construct a bootstrap confidence interval by applying the empirical or 95% rule. A 95% confidence interval is by far the most popular. Using the standard error method this week, all of the confidence intervals that we'll be constructing will be at the 95% confidence level. With the percentile method, you'll see other confidence levels. In Lesson 2, we learned that on a normal distribution, the middle 95% of observations will fall within about 2 standard deviations of the mean. This means that we can find the boundaries of the middle 95% of observations by taking the center, which is the mean of the distribution, plus and minus 2 standard deviation units. The formula for a 95% confidence interval is going to be very similar to this. It will be centered on the observed sample statistic, and then we will add and subtract 2 standard deviations, which on a sampling distribution is known as the standard error. This standard error and the observed sample statistic we can find using StatKey. This method can only be used when the sampling distribution is approximately normal. If the sampling distribution is not approximately normal, then the percentile method must be used, which we'll see next. It is possible to use the standard error method to construct confidence intervals at levels other than 95% if we have the appropriate multiplier. The multiplier of 2 is only used here because we're applying the 95% rule, and about 95% of observations fall within 2 standard deviations of the mean on a normal distribution. In Lesson 7, you'll learn more about how these multipliers can be found. Let's look at a couple of examples in StatKey of using the standard error method before moving on. I'll start with an example of estimating the difference in two proportions with a 95% confidence interval. I'll use the default data set, use of text messages by age. There are two age groups, adults and teens, and we're computing the proportion of each group that communicate via text message. The sample statistic that we're working with here is p-1, which is the proportion of teens who use text message, minus p-2, which is the proportion of adults who use text messages. Since the sample data are in and ready to go here, I'll start by generating 5,000 bootstrap samples just like we did earlier. Here's our bootstrap sampling distribution for the difference in these two proportions. This is approximately normally distributed, so I can use the standard error method to construct a confidence interval. The 95% confidence interval is going to be the observed sample statistic, so p-1 minus p-2, plus and minus 2, because we're constructing a 95% confidence interval, times the standard error, which is the standard deviation of this larger distribution. p-1 minus p-2, we can find in the original sample. This is 0.150 plus and minus 2 times the standard error, which we can get from the bootstrap distribution. This is 0.015. So our point estimate plus and minus the margin of error gives us a 95% confidence interval of 0.120 to 0.180. I am 95% confident that in the population, the proportion of teens who text is between 0.120 and 0.180, higher than the proportion of adults who text. Next, I'll do an example of estimating a mean with a 95% confidence interval. I'll use the weight data from my Minitab Express file. I'll edit data, select all, and delete the previous data, and paste in my weight data. Now I can see the original sample in the upper right. This includes the sample mean, which I'll need when I'm constructing my confidence interval. To get the standard error, I'll take 5,000 bootstrap samples. This bootstrap sampling distribution is approximately normally distributed, so I can use the standard error method to construct a confidence interval. This will be the observed sample mean of 172.222 plus and minus 2 times the standard error of 2.017. 172.222 plus and minus 4.034 gives me a 95% confidence interval of 168.188 to 176.256. To interpret this, I would say that I am 95% confident that the mean weight in the population is between 168.188 pounds and 176.256 pounds. I'll take you back to the PowerPoint slides now to move on to the next learning objective. Our sixth learning objective is to construct bootstrap confidence intervals using the percentile method in StatKey. This is my preferred method because it works with any bootstrap sampling distribution, even if it's not shaped like a normal distribution. The process for constructing the bootstrap sampling distribution will be the same here. The difference is that now we're going to find the boundaries that separate the middle 95% of the dots on our sampling distribution from the outer 5%. I'll take you back to StatKey now to walk through a few examples. I'm going to construct a confidence interval for the mean using the weight in pounds variable from my Minitab Express file. I'll copy that column from Minitab Express and in StatKey, edit the data. I'll select all and delete the previous data, and then paste in my new data. Like before, I'll take at least 5,000 bootstrap samples. Now this is where the procedure changes. The 95% confidence interval is going to be the middle 95% of these bootstrap sample means. In other words, the middle 95% of all of these dots. To find this, I'll select toTail. By default, StatKey will separate the middle 95% from the outer 5% of dots. At the bottom in the blue boxes, we have our lower bound and upper bound. To interpret this, I would say that I am 95% confident that the mean weight in the population is between 168.333 pounds and 176.292 pounds. Let's do another example, this time for a single proportion. I'll use one of the built-in data sets, Reese's Pieces Orange. On the right, I can see that in the original sample, 72 out of 150 Reese's Pieces were orange for a sample proportion, or p-hat, of 0.480. To construct the bootstrap sampling distribution, I'll take at least 5,000 samples and select toTail. The 95% confidence interval for the proportion of orange Reese's Pieces in the population is 0.400 to 0.560. I am 95% confident that in the population, between 40% and 56% of all Reese's Pieces are orange. What if I wanted a 90% confidence interval? I could change the proportion in the middle to 0.90. Now, the outer 10% of dots are red, and the middle 90% are black. My 90% confidence interval is 0.413 to 0.547. I am 90% confident that in the population, between 41.3% and 54.7% of Reese's Pieces are orange. As the confidence level decreased from 95% to 90%, the confidence interval got narrower. Similarly, if we wanted to be more confident, we could make this a 99% confidence interval. Now the interval is wider. In order to be more confident, we need to cover more of this sampling distribution. I'll go through one more example. I'll construct a confidence interval for a slope because we haven't done anything for a slope yet. I'll use the built-in marriage ages dataset again. We'll need to change the parameter from correlation to slope. This uses wife's age to predict husband's age. I'll take at least 5,000 bootstrap samples. For each of these bootstrap samples, the sample slope is being plotted on this bootstrap distribution plot. I'll select toTail Our 95% confidence interval for the slope is 0.971 to 1.181. If I were to construct this regression model in the population, I am 95% confident that the slope would be between 0.971 and 1.181. I'll take you back to the PowerPoint slides now to move on to the next learning objective. Our 7th learning objective is to construct bootstrap confidence intervals using Minitab Express. Minitab Express always uses the percentile method. This is a relatively new feature in Minitab Express. It's not available in Minitab 17 or 18. You must have Minitab Express to do this. I will say that I don't do this very often in Minitab Express because it will only take 1,000 resamples. In StatKey, you can take as many resamples as you want. I usually say to take at least 5,000. But in Minitab Express, the most that you can do at a time is 1,000. In both the Mac and PC versions, you can bootstrap a single mean, a single proportion, or the difference in two means. It does not yet offer the options to do the difference in two proportions, correlation, or regression slopes. I'll take you to Minitab Express now to walk through a few quick examples. On the Mac version, you'll have a resampling button, or you can find it in Statistics at the top. On the PC version, I'll go to the Statistics tab and Resampling. In this particular example, I want to construct a confidence interval for the mean height. So that would be one sample mean. I'll select height as the variable that I'm interested in. The number of resamples, you should always use the default as 1,000 because this is as high as Minitab Express will go. This is the number of bootstrap samples that it's going to take. If you think back to StatKey, this is the number of dots on that large bootstrap distribution plot. Under Options, I'm going to keep all of the default settings. In this course, we'll only be doing two-tailed confidence intervals, and the default confidence level is 95, which is most common. This is where you would change the confidence level, though, if you were asked for 90% or something other than the standard 95%. When we click OK, we'll get our output. First is the bootstrap histogram for height. This is comparable to the bootstrap distribution dot plot that we get in StatKey. The green number in the middle is the mean of this bootstrap sampling distribution. The red numbers are the lower and upper bounds of the confidence interval. Our confidence interval here is from 66.3912 to 67.2216. Minitab Express will also provide descriptive statistics concerning the original sample, and the bottom table has information about the bootstrap sampling distribution, including the number of resamples, the mean and the standard deviation, which is also known as the standard error, and finally the confidence interval, which matches the red numbers above on that histogram. I'll do one more example for the difference in two means. Let's say that we want to estimate the mean difference in height of males and females. I'll go to Statistics, Resampling, Two Sample Means. The way that our data are entered, both samples are in one column. Each sample in its own column would mean that all males would be in one column and then all females would be in a second column. Samples is the quantitative variable. Here, height. Sample IDs is the grouping variable. Here, biological sex. Again, I'll keep the default 1,000 resamples, and I'll use the default settings under Options. Our output looks similar. We start with a histogram. At the bottom, we can see that the variable being plotted here is the difference in means. By default, Minitab Express will do this in alphabetical order. And below, we can see that it says mean of females minus mean of males. Females tend to be shorter than males, which is why all of the values on our histogram are negative. The 95% confidence interval we can get from the histogram. It's the numbers in red, or we can look at the last table where the same numbers are presented. I am 95% confident that the population mean for females minus the population mean for males is between negative 6.9591 inches and negative 5.7525 inches. This takes us to our last learning objective. Describe how sample size impacts a confidence interval. Here, I have constructed two bootstrap sampling distributions using a hypothetical data set. On the left, n equals 10, and on the right, I tripled the data set to n equals 30. Comparing these two bootstrap distributions, the means are approximately equal. They should both be around the mean of the original sample. The standard errors are quite different. When the sample size was increased, the standard error decreased. With a larger sample, there's going to be less random sampling variation. This change in standard error impacts the width of the confidence interval. With a larger sample size, the confidence interval is narrower. This means that with a larger sample size, we can be more precise in our estimates of the population parameters. Another thing to point out here is the shape of the sampling distribution. As the sample size increases, the shape of the sampling distribution becomes closer to that of a normal distribution. The original sample here was skewed to the right. With n equals 10, the sampling distribution is slightly skewed to the right, though not as strongly as my original sample. With n equals 30, the sampling distribution is much closer to a normal distribution. I'll show you one more example of this, but now with a proportion. Both of these graphs were made with a sample proportion of 0.5. On the left, n equals 10. On the right, n equals 100. In each case, the mean of the bootstrap sampling distribution is close to the original sample proportion of 0.5. The standard errors are quite different. When n equals 10, the standard error was 0.159. When n equals 100, the standard error was down to 0.050. Again, as the sample size increased, the standard error decreased because there is less random sampling variation with a larger sample. The shape of the distribution also changed. On the left, with the smaller sample size, there are these big gaps between all of the possible outcomes. There are only 11 discrete possible outcomes here. In Lesson 7, you'll learn that this is similar in shape to a binomial distribution. On the right, with a larger sample size, there are more possible sample proportions. As the sample size increases with the proportion, the gaps get smaller and it starts to look more like a normal distribution. We'll study this again in Lesson 7. This concludes the Lesson 4 full video lecture. If you have any questions after watching this video or doing the readings, please post them to the Lesson 4 discussion board on Canvas.